I'm Andrew Jackson. I'm a geologist with Sprott, and I'm responsible for technical evaluations of the mineral companies and their properties that Sprott invests in. I've put together this Ore Deposits 101 series of talks to help non-technical people understand ore deposits, how they form, how they're explored for, how they're evaluated and mined, and how the metals and minerals are extracted from the ore. The talks give an overview of the main deposit types that investors in the resource sector may come across, and it covers many of the exploration and ore deposit evaluation process. This is the 11th talk in the Ore Deposits 101 series, and it focuses on the end point of the exploration process, mineral resources and reserves, and their estimation. The goal of the exploration program is to prove up resources and reserves and to estimate the value of what has been found. In short, to answer the question, can we make money from this pile of rock or not? Let me give some background to this question of resources and reserves. In 1969, the Vietnam War was in full swing and the demand for nickel was soaring. On October of that year, Australian junior Poseidon Nickel issued a release before the start of trading. Further to the report of recovery of nickel and copper and sulfides on September the 29th, the directors of Poseidon NL announced that the assays received to date of the first completed drill hole at PH2 at Windermere, Western Australia, are as follows. And they gave a table showing drill results with intersections broken down in feet, and nickel and copper assays to 2 decimal points. They continued, the consulting geologist Burrell and Associates Private Limited quote that the mineralized zone has an indicated length of 1,000 feet and minimum width of 65 feet. It was later shown that at the time of release, Poseidon's management had not received any assays from the lab. No details of the intersection width were available. It was total fabrication. Poseidon management awarded themselves options before the announcement, and Poseidon shares ballooned to almost 35,000% of their IPO value. Management exercised and sold the options before they revealed that the data was far too sketchy to draw any conclusions. When the actual assay results were released, they were shown to have been hugely overstated, and with subsequent poor results, the bubble dramatically burst. Now, it took ASA regulators nearly 20 years to do something about this problem, but in 1989 they incorporated the first version of JORC, Joint Ore Reserves Committee, code into ASX listing rules to standardize the method of reporting resources and reserves. Then in 1997, the Bre-X scandal exploded onto the Toronto Stock Exchange. For those not familiar with the story, Canadian David Walsh started a company called Bre-X Minerals in 1989. But by 1993, he and his wife were declared bankrupt. That same year, Bre-X Minerals bought the rights to Busang property in Kalimantan on the basis of a few anomalous grab samples. Walsh hired a Filipino geologist, Michael de Guzman, to oversee exploration. Not much happened over the next 2 years, but in 1995, reports of spectacular drill results began to be released. Over the following 2 years, the resource estimates grew to 30 million ounces of gold, then to 40 million ounces, and then to 71 million ounces. The share price climbed exponentially, and the big mining companies were falling over themselves to get a piece of the action. However, they were having difficulty getting access to the project to carry out due diligence. In February 1997, there was a suspicious fire on site that destroyed most of the maps and assay sheets. But that didn't stop Bre-X from announcing that the resource could eventually reach 200 million ounces. Shortly afterwards, Freeport was finally able to get in site and re-assay core. And Freeport reported soon after that, to date, analyses of these cores, which remain incomplete, indicate insignificant amounts of gold. the Bre-X bubble burst, and the share price tumbled. Michael de Guzman was reported to have fallen from a helicopter, although his body was never conclusively identified. Now it was the TSX's turn to be embarrassed, and something had to be done. The following year, the TSX set up a task force with the mandate to repair investor confidence by ensuring that there were adequate standards and disclosure procedures. That resulted in a 7-year discussion between industry and players and regulators. In December 2005, National Instrument 43-101 became effective. The Australian JORC and Canadian 43-101 regulations are very similar, although the 43-101 is a bit more stringent on what must be disclosed. In basic terms, both state that a company can't disclose the tons and grade of a deposit unless it has been classified either as a mineral resource or reserve. Resources become reserves as more data is required and confidence improves. Only 5 categories of resource and reserve are acceptable. For resources, these are measured, indicated, and inferred. For reserves, they are proven and probable. Reserves must have at least a pre-feasibility to back them up, and I'll talk more about feasibilities later. Now I know that the next 2 slides on definitions on each of these is probably going to be very boring to many of you, but it is important, so please bear with me. We'll start with a definition of the various categories of mineral resources. The key phrases are underlined. A mineral resource is a concentration of minerals that has reasonable prospects for economic extraction. Location, quantity, grade, and continuity are interpreted from geological evidence by a QP. Inferred mineral resource, one of those subcategories, that part of a resource for which quantity and grade or quality can be estimated from a geological evidence, limited sampling, and reasonably assumed geological and grade continuity, based on outcrops, trenches, workings, and drill holes. It must be excluded from estimates for economic studies. The next one up from that is the indicated mineral resource, which is that part of a resource for which quantity, grade, or quality can be estimated with sufficient confidence to support mine planning and evaluation of the economic viability. It's based on outcrops, trenches, workings, and drill holes that are close enough for grade continuity to be reasonably assumed. The top one in the resources is the measured category, and is that part of a resource for which quantity, grade, or quality can be estimated with sufficient confidence to allow production planning and the evaluation of economic viability. It's based on outcrops, trenches, workings, drill holes that are spaced close enough to confirm both the geological and grade continuity. Moving now on to the reserves. Mineral reserves are economically mineable part of a measured or indicated resource and demonstrated by at least a PFS that includes adequate information on mining, processing, metallurgical factors, etc. to demonstrate economic extraction can currently be justified. And that word currently is very important. It has to be under current economic conditions. Reserves include diluting materials that allow for losses during mining. And it's subdivided into probable and proven reserves. The probable reserves are the economically mineable part of an indicated resource, and sometimes in a measured one as well. A proven mineral reserve is the economically mineable part of a measured resource. If you're like me, a picture is worth 1,000 words, and this table summarizes resources and reserves. Projects rise up the y-axis as work improves geological knowledge and confidence, and they move across the x-axis with the addition of mining, metallurgical, economic, marketing, legal, environmental, social, and governmental studies. Note the other arrows in the middle of the center and show how they may change. Inferred resources cannot move directly to probable or proven reserves. They have to increase to measured or indicated resources before they can be converted to reserves. Okay, so that's got the definitions out of the way. Now let's move on to something a little bit more interesting. That's turning our raw exploration drill data into something useful. Something that can eventually lead to the decision as to whether it makes economic sense to mine it or not. As you would imagine, there are a number of steps that a project has to go through. This slide summarizes those steps, and we'll go through each one, starting with the collection of geological information. The first step is to collect all the exploration data to select what can and what cannot be used in the next step, which is the building of the geological model. Most of the data collected during the long process of exploration is used directly or indirectly in defining the geological model. Geological mapping, rock chip samples, trench data, geophysical data, and drill log data may all assist with defining that geological model. Soil sample, although it's really useful in identifying drill sites in the early part of an exploration program, is not actually much use in defining the geological model. Once all the exploration data is compiled and the useful data sets are selected, we can build that geological model. The geological model reflects the geologist's understanding of the mineralization, its host rocks, and its structural deformation. The geological model is built using 3D modeling software. The most important data comes from geological mapping and the drill database. But other soft data can also be used, and integrating this requires the modeler to use both a mix of data and geological intuition. His aim is to define three-dimensional envelopes that reflect characteristics that may impact on economics. For example, the erosion surfaces, geological contacts, or faults. And one of the most important features he needs to model is the mineralization envelope. These features will all have direct influence on either the limits of the mineralization or on mining or processing costs, such as rock density, hardness, or the degree of weathering. The mineralization envelope defines the outer limits of the mineralization. It may have hard boundaries where the mineralization is known to be cut off sharply by, say, a fault, or soft boundaries which define the outermost portions of a gradational fading out of the mineralization. In the case of soft boundaries, the ultimate limit of the mineralization will be defined later using geostatistics to define where the grade drops below the applied cutoff. The mineralization envelope is sometimes divided into separate domains that have different characteristics and need to be treated separately. There's no point in building an unnecessarily complex model showing every geological contact that may have been identified. If two rock units have the same mining and milling characteristics, they may be clumped together to simplify the process. Once the geological model is complete, we move on to producing a grade model. Key to this process is the so-called qualified person, or QP. The QP is defined as an approved engineer or geoscientist with at least 5 years of experience, who is knowledgeable of the mineral property concerned and who has sufficient experience and qualifications to make the statements which are made within the report. He or she also has to be in good standing with a professional association and of recognized stature within that organization. The QP uses his professional judgment on a number of calls during the evaluation process, and it's his professional and ethical reputation that's on the line when he puts his name to a resource estimation. The first step in constructing the grade model is to superimpose a digital 3D block model or framework onto the geological model, selecting block dimensions that allow sufficient sufficient detail This is obviously a very coarse block model that I have in the illustration, and it is just for illustration. A real block model may have hundreds of thousands or even millions of blocks. The dimensions of the blocks depend largely on the size and the shape of the order envelope, and it may vary within the model. Having established the framework, we take the available assay data and extrapolate this to assign an estimated grade to every block in that grade model. Producing a grade model is a somewhat more restricted step than building the geological model. Not all the data that is collected during the long process of exploration and is useful in building that geological model can be used in defining the grade model for resource estimation. For example, chip sample assays cannot be used in a grade model. Likewise, not all drill samples, such as those from air core, can be used. Air core assays are not considered sufficiently representative of grade distribution due to their tendency to smear values. Data from RC and diamond drilling generally are acceptable. Even underground channel sampling may be considered acceptable in certain cases. Before it is incorporated, any data set needs to be carefully verified and any errors corrected, a process known as data cleaning. Now, in grade estimation, the process of extrapolating from the drill data to fill each of those blocks in the model has a fundamental problem that has to be overcome. A diamond drill core may have a diameter of, say, just 48 millimeters, and yet we're trying to extrapolate that to fill a block that may be tens of meters in each dimension and into adjacent blocks as well. Drill core may comprise just 1/100th of a single percent of the ore body. So we're back to that same simile that we came across in an earlier talk. The group of blind men trying to describe an elephant from the small portion that they can feel. Fortunately, in the case of estimating grade, we have a series of geostatistical tools that can be used to assist. What is estimation? It's the process of using sample data to predict the most realistic distribution of grade, or it could be lithology or specific gravity or any other feature throughout the mineralized body. The only thing we know about our final grade model is that it will be wrong. We can never know the precise grade and distribution in any ore body until it's been completely mined out, and then it's too late to be of use. However, geostatistical estimation can give us a reasonable idea of grade distribution in 3D, hopefully good enough for us to base our financial calculations on it to allow a sensible go or no-go decision. There are a multitude of geostatistical estimation methods. At the risk of being shot by those for whom geostatistics is their daily bread and butter, I will describe just 3 of the more common methodologies: polygonal, inverse distance, and kriging. I'll start off with the polygonal methods. Polygonal estimations are very crude and rough and ready. There are several variants, but basically they take known data points and then construct areas of influence around them, assigning the grade of the sample point to the entire 2- or 3-dimensional polygon. Here's a real-life example of a polygonal estimate. Polygonal estimations are most commonly applied to planar vein-type deposits. Here's another way to build up a polygonal method, with the average grade of the 3 samples at each corner of the triangles being applied to the polygon. The advantage of polygonal methods is that they're quick, cheap, and can be done with sparse data sets and minimal geological understanding. The disadvantages are that they don't take into account geological trends, and they tend to overemphasize the occasional high-grade samples. Polygonal methods are so crude that, with easy access to 3D software that incorporates relatively sophisticated statistical code, they're really seldom used now. The next step up are the inverse distance or ID methods. This estimation method assumes that the closer together two samples are, the more likely they are to be related. Using the straight inverse distance variant, if sample A is half the distance from the block to be estimated than sample B, then sample A will have twice the weight of sample B when assigning that grade to the block. In practice, simple inverse distance still suffers from the same overemphasis of isolated high-grade samples that the polygonal methods suffer from. So ID squared or ID cubed are more commonly applied. These limit the spreading of their high grade. The advantages and disadvantages of ID methods are really very similar to those of the polygonal methods, although not as severe. Kriging is by far and away the most commonly used methodology today. It's named after a South African mining engineer, Danie Krige, who conceived the mathematical concept in his master's thesis. Like ID, Kriging uses the weighted average of neighboring samples to estimate the unknown value at a given location. But unlike the earlier methods, it takes into account the directional trends that sampling exhibits, so that assays of samples in certain directions are weighted more heavily than those in other directions. Kriging is a two-stage process. The first stage is to establish the predictability of sample values by comparing each sample with every other sample in the dataset. To do this, the computer plots each sample pair in a certain direction on a graph of distance apart on the x-axis and against the variability of the pair on the y-axis to produce a semi-variogram. Then a best fit line is fitted through the points. The leveling off of the curve gives a measure of the distance that a sample assay can be reliably extrapolated in that direction, in this case just 3.8 meters. The process is repeated for other directions, and the combination of these semi-variograms defines a search ellipse showing how to weight samples in any particular direction. The second stage of the Kriging process is to apply the search ellipse to estimate the grade of unsampled subblocks. This is done by taking the earlier defined geological model with its superimposed empty block model and estimating grade within each cell of the block model, using the ellipse to determine which assays are used in the process and how they'll be weighted. Note that Kriging also provides a standard error to quantify confidence levels, which may be important in classifying blocks as measured, indicated, or inferred. There are a number of variants of Kriging, including simple, ordinary indicator, and multiple indicator. The geostatistician will make a call as to which type of Kriging is best suited to the dataset. In general, the simplest variant that is suitable for a particular dataset should be used. Multiple indicator Kriging is one of the most arcane. It was used by Snowden at Pretium's Brucejack deposit and generated huge controversy. But in this case, MIK was justified by the unusually nuggety distribution of the gold in the Brucejack deposit. The advantages of Kriging are that it takes into account the real geological trends displayed by the samples, and also that it provides a measure of confidence for each estimated block. The disadvantages are that it is time-consuming and tends to smooth the data somewhat. Individual blocks in the block model are not only tagged with an estimated grade. Any number of characteristics can be attached to the blocks, such as the rock type, the rock density, and hence tonnage, metallurgical characteristics, rock hardness, which is of interest both to the mining engineers and the metallurgists, metallurgical recovery, and so on. Basically, any factor that has a bearing on the cost of the mining or the cost of extraction of the metal should be included in that block model. Now we've built our block model that includes the grade, we can use that to estimate a resource. You will remember that the definition of a mineral resource is a concentration of minerals that has reasonable prospects for economic extraction. So first we need to work out what the likely economic cutoff is, using an assumed metal price and the probable cost of mining and milling. Mining and milling any grade lower than this economic cutoff will result in an operating loss, so only blocks with a grade of greater than the cutoff are used in the resource. The tonnages of the remaining blocks are totaled, and their weighted average grade is calculated to produce a total resource. Based on the kriging confidence and other factors that the QP deems important, this resource is divided into categories. Each of the blocks will have a measure of confidence assigned from the kriging, which is useful in determining whether to classify them as measured, high confidence, indicated, lesser confidence, or inferred, very low confidence. Measured and indicated are often clumped together in reports, as they can be used in a pre-feasibility study. Inferred resources are considered too vague to be used in a pre-PFS, but they can be used in the less rigorous scoping study. Although the definition of resources states that they should have reasonable prospects for economic extraction, when they could be economically extracted is not defined. What we need to know is, are the resources practically and economically mineable under current economic conditions? Do they meet the requirements to be classified as reserves? Very often the answer is no. For example, this low-grade mineralization at depth is probably currently not economic. To define reserves and produce a feasibility study, we need more information than we currently have, and we'll need to carry out additional studies to collect that necessary data. This data collection is normally done in 3 stages of increasing detail. The lowest level of detail is the preliminary economic assessment, or PEA, also sometimes called a scoping study or an order of magnitude study. This plugs in the first economic assumptions to see if the project makes any economic sense at all. Inputs are rough, usually within 40 or 50%, and usually on the optimistic side. So PEA, although giving a useful first idea of the viability of a project, should be taken with a pinch of salt. The next stage is the preliminary feasibility study, or pre-feas or PFS as you'll sometimes hear it called. This includes more detailed metallurgy data, including the processing method, associated capital, operating costs, and percentage recovery. It includes rock mechanics information to determine the pit slope stability and the angle of pit walls. In engineering data, including the mining method, initial power and water requirements, their sources, and capital and operating costs, as well as softer social issues and costs. Cost estimates are generally plus or minus 20 to 30% for a PFS. The third stage, that will take us to the point where a construction decision can be made, is the feasibility study, sometimes also called a full feasibility study or a bankable feasibility study. They're all the same. This includes tightening up on all the above data to within 15% accuracy. It also includes an environmental impact study, or EIS, socio-political studies, legal, tax, and financing details. Once the PFS data have been collected, a reserve estimate can be derived. At the risk of repeating myself, reserves are mineable at current economic conditions. Portions of the resource are converted to reserves based on the practicality of mining, economics of extraction, mining dilution and recovery factors, and metallurgical recovery. The resource statement may or may not include the converted reserves. Check on this when you see both quoted to avoid double dipping. Generally, indicated resources convert to probable reserves, and measured resources convert to proven reserves. The reverse is also true, however, and probable reserves can be downgraded to indicated or measured resources if additional information warrants this at a later stage. As a general rule of thumb, anything from 40 to 80% of a resource will eventually convert to reserves. If you see a figure that's outside of this range, the resources were either highly over-optimistic or seriously under-drilled, and both of these are warning signs. In the case of the deposit that will be mined from underground, reserves are derived by defining practical underground stopes based on the grade block model. This is usually done by hand by a mining engineer using cross-sections. He outlines what can be practically mined based on the defined cutoff grade and physical mining constraints. These sections are then merged in 3D to form the outline of the planned stope. The blocks that fall within the planned stopes can then be totaled to form the basis for a reserve statement. In the case of a deposit that will be mined by open pit, most of the process is done by computer nowadays, using mathematical algorithms to define the best pit shapes for multiple economic scenarios. This process is called pit optimization. Most pit optimization software is based on the Lurch-Grossman algorithm, or the floating cone method. This was most successfully applied by Jeff Whittle back in 1990, and you may hear engineers and geologists talking about a Whittle pit. The algorithm calculates the profit or loss for each block in the model, taking into account which other blocks need to be mined to get to the block in question. To illustrate this process, let's look at a simplified example using just a single vertical 2D slice through an imaginary block model. The numbers in the blocks show their in situ value, based on their grades and a selected metal price. I've color-coded them to represent this in situ value. At the top of the model is the ground surface. Now assume blocks cost 1 unit to mine, so that our rock mechanics experts have said that the rock will withstand 45-degree pit slopes. Starting on the top left and moving along the top line of blocks, no blocks have any value until we reach the first yellow block. This block has a value of 1 unit, but it would cost 1 unit to mine, and so it has a net profit of 0, and it's not worth mining by itself. The orange block next to it, however, has a value of 2 units, and it would cost 1 unit to mine, so it would give a profit of 1 unit, and so it would be selected for mining by the algorithm. I'll mark it in bold. Continuing to move right along the top line, no blocks have any value until we reach the last yellow block. The computer then starts on the second row of blocks. The first orange block has an in situ value of 2, and to mine it would cost 1. However, using 45-degree slopes, the 3 blocks above it would also need to be mined, adding the 1 unit credit from the yellow block directly above it, which is not yet mined. The orange block above and to the right has already been mined and so is ignored in the calculation. That gives a total cost of 3 units to mine it, with a total in situ value of 3. So the total profit of mining this block would be 0. And the algorithm does not flag it for mining and passes along the row to the next block. This purple block is a high-grade block worth 4 units. Again, the 3 blocks above it need to be mined, but the orange block has already been mined and is ignored. So the total in situ value of these blocks is 5 units. Total cost to mine is 3 units, giving a profit of 2 units. The block and those above it are therefore flagged to be, and so on across the row, flagging those blocks that are profitable to mine. until we come to the third row. This time, each block requires 8 blocks above it to be mined, but some of these have already been mined or tagged for mining and are ignored. Remember that although we are only showing this in 2D, the algorithm is actually calculating in 3D. So each of these triangles of blocks to be mined is really cone-shaped. That a floating cone that is sometimes applied to this process. The process continues layer by layer, steadily building up the shape of the optimal pit at the selected metal price and cost of mining. As you can see, as we get to deeper blocks, the number of blocks that need to be mined increases exponentially. Obviously, this doesn't matter too much in the center of the pit, where many of the overlying blocks have already been tagged for mining. But it has a huge impact on the edges, where blocks with minimal value are having to be removed to expose the worthwhile blocks. And very soon the stripping ratio overwhelms the value of even the high-grade pods, and no more blocks can be mined. The final pit is outlined by the blocks that have been tagged for mining, and mining this pit will provide the maximum operating profit. As I mentioned, remember that this optimization is done in 3D. A real block model may have well over 1 million blocks, but the same principle applies. Now, once we have a pit to constrain the resource, and current and realistic costs and prices have been applied, we can convert some of those resources to reserves. In fact, the pit optimization process doesn't produce just a single pit. It produces multiple nested pits, each shell representing a different financial scenario. Because it is beneficial to start mining the most profitable pit first, wherever possible, these nested pits are incredibly useful as they show the most profitable pit shell, blue in this particular diagram, that can be mined as a starter pit, and then a series of other pit shells that can be mined consecutively with pushbacks to the wall at each new phase. It also allows a series of what-if scenarios to be run to see if their effect on the discounted cash flows. However, remember that the inputs of a Whittle run are operating costs and product prices. Capital costs are not factored in and have to be applied separately. The most profitable Whittle pit shell may not be so profitable when the cost of capital is included in the mix, due to the stepped capex increases as throughput is increased. Taking account of the capital costs takes place during the scoping and pre-feasibility studies, but it's refined during the feasibility study. Now we come to the last step, the feasibility study. Armed with the reserves, all the figures used in the PFS are then tightened up so that the costs are to within plus or minus 15% accuracy. Facets that were only touched on in the PFS, such as the environmental and socio-political issues, are dug into in great detail, and an EIS or environmental impact study is compiled and submitted to the relevant authorities. All legal and tax implications are studied minutely. Financing possibilities are discussed with banks. Heads of agreements may be drawn up for power and water supply, and offtake agreements may also be negotiated. The objective of the feasibility study is to provide a tool that management and investors can examine and use to make a go or no-go or an investment decision. The reliability of feasibility studies has improved thanks to the NI 43101, but even so, the fact that the project has completed a positive feasibility study does not guarantee that it will be developed. There are plenty of positive feasibilities on projects that are not economic, and investors need to be very careful of taking published feasibility studies at face value. They need to dig into the detail to see if the underlying assumptions that have been used are indeed realistic. Mark Twain's description of a mine being a hole in the ground with a fool at the bottom and a liar at the top is a bit harsh, but like most industries, there are plenty of crooks out there. The 43-101 process is designed to make it harder for those crooks to operate, but it's not foolproof. A feasibility study is simply a tool to assist in the go or no-go decision. It's a means to an end. It's not an end in itself. So let's recap quickly the points that we covered in this talk. The mining industry is now better regulated thanks to the JORC and the 43-101 regulations that companies have to follow. The regulations make the evaluation of properties more transparent and standardized, but they're certainly not foolproof. A project evaluation follows these steps. Collect geological information, including mapping, geophysics, and drilling. Build a 3D computer geological model to display the extent of geological units that are significant for mining or processing. Superimpose an empty block model and extrapolate the drill data to produce a grade model using the geostatistical methods such as inverse distance or kriging. Determine the resource, dividing into measured, indicated, and inferred categories according to confidence levels. Acquire mining, metallurgical, economic information to be able to make the basic economic assumptions. Remember, a PEA has an accuracy of plus or minus 40 to 50%. A PFS has an accuracy of plus or minus 20 to 30%. Also remember that a PFS can only use measured and indicated resources. Determine the reserve by designing stopes or optimizing a pit and including only those resources that fall within inside the mining plan. Use those reserves and improved costing data to within 15% now as the basis to produce a feasibility study. And finally, we come to the construction decision, remembering that a positive feasibility study does not necessarily mean a positive construction decision. So that's a highly simplified run-through of the evaluation process to help us answer the question I posed at the beginning of the talk. Can we make money from this pile of rock or not? That's the end of this talk, and thanks for taking the time to watch.